Today, we're going to pull back the curtain on something you've probably never heard of, but it's basically the secret sauce behind the UK's entire green energy transition. We're talking about the super detailed, number-crunching work that decides where billions, with a B, of pounds get spent on our national power grid.
So let me ask you something that sounds a bit crazy. Why on earth would we ever turn off a wind farm on a perfectly windy day? I mean, we're in a race to get more green energy, right? So paying a wind farm to just stop feels totally backwards. But believe it or not, this is a real thing, and it points to the exact problem that grid planners are desperately trying to solve. And the answer? Well, it has less to do with the weather and everything to do with the physical limits of the grid itself.
Okay, so we're going to tackle this in 5 simple steps. First, we'll look at what I'm calling the green energy traffic jam. Then, we'll uncover the invisible tool engineers use to measure it. After that, we'll get into the big debate, planning for security versus planning for cost. We'll even see how they stress test the whole system. And finally, we'll tie it all together to see how this brainy analysis actually helps build the grid of tomorrow.
All right, first up, the green energy traffic jam. See, the biggest challenge we have right now isn't just making green power. The real headache is getting that power from point A to point B.
So think about where we're building all this new renewable energy. The UK is going all in on wind power, especially these huge offshore wind farms. And where's the best wind? Way up north, mostly around Scotland. But here's the catch. For, a century, all our big cities and factories, the places that actually use all that electricity, they're clustered down in the south.
And the best way to wrap your head around this is to stop thinking of the grid as just a bunch of wires. Instead, picture it like a massive web of motorways, but for electricity. These giant high-voltage lines are the country's arteries, designed to pump huge amounts of power from where it's made to where it's needed.
But here's the thing. Just like the M25 on a bank holiday, these electrical motorways can only handle so much traffic. So when all that amazing wind power from Scotland tries to surge south to London, you get a traffic jam, a massive bottleneck. And when that happens, that cheap green electricity has literally nowhere to go. The system operator has no choice but to tell the wind farm to power down. They call it curtailment. And to keep our lights on, what do we have to do? We have to fire up older, more expensive gas plants down south. It's the worst of both worlds. We waste clean energy, and it costs all of us money. It's a huge problem.
So, the big question is, how do you manage a traffic jam on a motorway you can't even see? Well, engineers have a really clever tool for this, and it's called a power system boundary.
Now, a boundary sounds complicated, but the idea is actually super simple. It's not a physical thing, like a wall or a fence. It's a conceptual line that an engineer draws on a map of the grid, right across a critical corridor of power lines. You can almost think of it like a virtual tripwire or one of those traffic counters they lay across a road. It just sits there, invisibly, and counts every single megawatt of power that flows past it. This lets engineers see, in real time, exactly how congested that electrical motorway is getting.
Okay, so measuring the traffic is one thing, but deciding how wide to build the motorway in the first place, now that's where things get really interesting. And this gets us right to the heart of a huge debate in grid planning. It's this constant balancing act between two totally different ways of thinking.
See, the official rulebook basically says engineers have to plan for 2 completely different futures at the same time. On one hand, you have demand security. This is your classic prepare for the worst plan. Picture this. It's a freezing cold, dark winter night, demand for power is through the roof, and there's not a breath of wind, no sun in sight. The goal here is just pure, raw resilience, making sure the lights stay on no matter what. But then, on the other hand, you've got the economy plan. This is all about planning for the future we want, a future where we're running on as much cheap green energy as we possibly can. The goal here is all about efficiency, making sure the grid is big enough to handle all that renewable power without causing those expensive traffic jams. And the crazy part is, the grid has to be built to handle both of these scenarios.
But it doesn't stop there. Just planning for those 2 scenarios isn't quite enough. To really understand what the grid can take and to make the case for building more of it, engineers have to find its absolute breaking point. They have to, metaphorically push it till it breaks.
And they do this with a really cool computer technique called scaling. You can basically think of it as a virtual stress test for the entire grid. They build this incredibly detailed digital twin of the national grid, and then they just dial up the pressure on one of these boundaries until something in the simulation goes pop.
So here's how it works. They start with a normal day on their computer model.
Then, bit by bit, they start cranking up the power flowing across that boundary. They'll virtually turn up the wind farms in the north and at the same time turn up the demand for power in the south. After every little push, they run a massive simulation, checking everything. Are any wires getting overloaded? Is the voltage stable? Is the whole system about to collapse? They just keep pushing and pushing, megawatt by megawatt, until something finally breaks. And that number, right before it all goes wrong, that is the magic number. That's the boundary capability. It's the absolute definitive maximum amount of power that corridor can handle, period.
And this is where it all comes together. Because all of this high-tech digital wizardry doesn't just stay inside a computer. Oh no! It's the thing that directly triggers real-world action. We're talking decisions involving actual concrete and steel.
Look, the numbers that pop out of these boundary studies aren't just numbers on a spreadsheet. They are the hard evidence used to justify spending billions, and I mean billions of pounds on our national infrastructure. They're the reason a new power line gets built in one place and not another. It's that important.
You know, there's a quote in the official planning documents that just nails it. It basically says that these boundary studies are what directly inform strategic investment decisions. In plain English, they tell us exactly where we need to strengthen the grid to keep our power secure, affordable, and reliable as we push towards that green future.
This really is where the rubber meets the road. This analysis isn't some academic exercise, it's the actual toolkit for building our net zero future. It answers the really big practical questions, like where are the absolute worst bottlenecks in the country? If we spend a few billion on a new power line, how much extra traffic can it really handle? It lets us compare massive, expensive projects against each other to see which one gives us the best bang for our buck. This is, quite literally, the technical roadmap that tells us what we need to build to hit our climate targets.
Which, of course, leaves us with the million-dollar, or rather multi-billion-pound question. This whole thing isn't just a technical puzzle for engineers. It's a massive strategic challenge for the entire country. As we race towards a green future, how do we get that balance just right? How do we build a grid that's secure, a grid that's affordable, and do it all fast enough? That's the incredible puzzle that these boundary studies are helping us to solve 1 megawatt at a time.